If you look at, say, these two purple dots right here in the middle, kind of intermediate-sized purple dots, you could easily look at those two dots and say, yeah, they're the same. They're the same species. There's slight variations in that population, microevolution at work there. Same with these two, or these two, or these two out here. Where any two neighboring dots here, you can look at as just minor little changes. And it doesn't take a lot to imagine that all those little changes added up over time do the same thing as this. This is a much more realistic story. And this is what we actually see happening. All right. Okay, so you may have noticed though, if we're going to say that this is one species and this is another species, these two extremes of the range here, and we're going to say that these two are the same species and these two are the same species, and all along each neighboring one is the same species, where do we draw the line? Where's the difference between that little species and that big species? And that's a good point. That's a good question. If you were thinking that, you're on the ball. What the problem is actually this kind of reveals a problem with the whole concept of a species. Because when we look at organisms, we don't see this. We see a snapshot. We see one of these. And when we look at something that's alive today, or we look at something that's in a fossil, what we see is a snapshot in time of this sort of gradient. Now, that problematic, this has gone to sleep, and I don't know how to, there we go. So we do see this same kind of idea of hard to define species. Okay, so this is an example of what we call a ring species. And a ring species sort of illustrates that same point that we were just talking about. These are salamanders, Encentina salamanders that live historically lived up in Oregon and Northern California, and migrated or began to move slowly down into California. And as they did so, they couldn't really populate the Central Valley of California. It's not a hospitable environment for them. So they went on either side of it. And what you get is we actually have 7 different subspecies here of this same salamander species. And we consider them the same species because even these ones down here at the bottom are similar enough to these ones up here that they can breed with each other. And the reason for that is because they can breed with that one, and they're similar enough to breed with that one, they're similar enough to breed with that one, and those ones are similar enough to breed all the way up the coast. Salamanders don't get around a lot, they don't fly, they don't migrate long distances, so they keep that gene flow pretty small, but it's enough within these little populations that it keeps them all the same. But the gene flow going on this side has been different from the gene flow going down this side, down the inland route here. The point that I'm making is at the bottom of these forks, these species, these two different subspecies, cannot reproduce with each other. They are basically distinct species. As you follow down the coast of California, or down California, follow this population down, you see speciation happening. You see a parent population diverging into 2 distinct species. And if these were to completely break off from each other, a new highway system develops here, or river, or mountain range or something, you could see that we would have 2 distinct species, completely different animals. And you can see where they came from originally. And it's not just salamanders. The next slide. This happens a lot of species. Arctic gulls, mole rats, deer mice, greenish warblers around the Himalayas, these North American bees. This is a fairly common thing that happens. What's next? All right, so let's get into the fossil record in a little bit. I got a question. Does anybody have a guess, or does anybody know about how many species there are alive on the planet today? Millions. You want to be more specific? You're right. About 2 million? 2 million is a low estimate. We've identified and labeled about 1.5 billion, 1.4 million. Their estimates are there are actually probably about 10 million species. So let's see, 10 million. Bing! I feel like okay. Does anybody have a guess how many species have ever existed on this planet? This is hard. One species? I'm going to say that's probably not right.
80% has already been extinct.
All right, let's see. It's about 10 billion. And now this is a harder one to estimate. And estimates actually range from about 1 about half a billion up to about 20 billion. 10 billion is pretty safe estimate though. How many? Yeah, okay, go ahead. We've got about 250,000 fossil species that we've actually found and identified. Now that's a lot, if you think about it. That's definitely enough to keep scientists busy for a long time, studying those 250,000 species. But if you compare that to that number, 250,000 to 10 billion, it's almost nothing. It's actually about 99.99%, it says on the next bullet, of the extinct species have not been discovered. That's a lot of information, a lot of data that we don't have. Why? Well, fossilization is a pretty rare process, a pretty rare thing to happen, a pretty rare phenomenon. It's very, very difficult. It takes a very long time. And because of that, not every animal that dies is going to become a fossil. All right? If you think about something like a slug compared to something like a snail, you can see that the snail's got a nice hard shell. That hard shell is something that's going to fossilize a lot easier than the slug. But most snails will never fossilize either, if you think about it, because most of them that die are going to get eaten by something, either predators or after they die, they'll get eaten by scavengers, they'll get crushed or something. Most animals that die don't even make it to the stage where their body could be fossilized. If they do, they have to basically die in the right place, where they're going to basically be either buried by something or undisturbed for long enough for them to actually be buried. And that's pretty rare. And, it's basically something that doesn't happen. We're actually very, very lucky to have any fossils. So, but we do have fossils, and they do tell us a story. So let's look at this little background information here before we get into what this all means. These strata, or what geologists like to call layers of the earth, of the rocks that you look down into. This is kind of a weird photo, a weird picture. It's just a sketch, but all these fossils kind of embedded in it. And this is what obviously people have understood for a long, long time. It goes back to the late 17th century, late 1600s, was when people first realized that this wasn't all just poof, there it is. And that was what they thought beforehand, was that all of those layers were created exactly as they are, with the fossils embedded in them, all at once. And someone took a look at that and said, that doesn't quite seem right. This guy here is fossilized there. That probably was walking around on the ground at some point and then was buried, which means he was buried under this layer, and this layer was laid down on top of that layer. And the implication of that is that the further down you go, the older the rocks are. And with that understanding in mind, geologists began to reconsider the layers that they knew about around the world, and had already kind of started to label and identify. But now knowing that they're older, they started to look at the patterns that they find in those layers, in both the type of rock and the fossils that are found within them. And began to realize that we actually see patterns emerging in those layers, and in the fossils within them. So one of the things that they start to see, let's go to the next thing, the big transitional forms. And I'm sure that we're going to have a lot to talk about transitional forms today. What is a transitional form, though? You may think you understand it, but when you get into it, let's see the first definition. First definition is an organism that is intermediate between an ancestor and a descendant in an evolutionary sequence. That's the first. I looked these up online, this is the first one I found. Next one, I found this on Wikipedia. Forms of life that illustrate an evolutionary transition. They can be identified by their retention of certain primitive traits and with their more in comparison with their more derived relatives. What that means is that you're looking at basically animals that have some traits of newer animals and animals that have some traits of older animals. So they may look a little like their ancestors and a little like the subsequent animals, the more modern animals. It may not be easy to see the difference between these two, but there is an important difference actually. This one sets up an impossible standard. This one on the left basically says that we know that that animal, that organism, is in a direct line. We know who its parents were, we know who its offspring were. And that's impossible. We can never know that from the fossils. So this is actually not a definition we can even use to begin looking for transitional fossils or transitional forms. This is the definition that we use. Now, when Darwin wrote The Origin of Species, he wrote this into it. He said that the lack of transitional fossils may be the most